Hi, and welcome back to another edition of Night Chemistry, Gas Laws number one. Let me turn that off so we're not echoing. Gas Laws day one. This is to follow day zero. Day zero was, remember the day we got you set up to explore a little bit, some of the documents I already set up, some problems and things like that related to gas laws, get you some notes started, and then begin the foldable, which we'll just kind of run through the contents of very, very quickly. So, without further ado, let's go. So, kinetic molecular theory is the next slide, or is the first slide that we come to. Is on the back of your foldable. Kinetic molecular theory is exactly what it says. It's about regarding motion of molecules, right? It's a theory about it. It says that particles are always in some sort of motion. In fact, we have here this: particles are always in motion. The fact that they are in motion means that they're basically not occupying space at any point in time for very long, or long enough to make a difference. So we can calibrate. Anyway, the volume is essentially zero, is what that turns out to be. So let's keep on going with that. Collisions of particles with the container walls cause the pressure of the gas itself. Oops, whoa. There we go. Cause the pressure of the gas. Particles exert no forces on each other, okay, even though they're going to slide past and collide and stuff like that, but they don't exert any continual forces that are working. And then the average kinetic energy of all of that motion, average kinetic energy or kinetic energy is the energy of motion, so it's related to its velocity, how much it's moving around, is related to the Kelvin temperature of a gas. Kelvin temperature is just the mathematical temperature of gas. It's the mathematical temperature that we can use in math. We can solve math problems of temperature using temperature if it's in the Kelvin unit. Kelvin is another unit for temperature if that's new to you. And then what we gleaned from that the other day is that basically this just means that we can make an equation that relates kinetic energy, Ke, as it's commonly called, or just E with a subscript K, is somewhat proportional to that. Basically, the little Jesus fish, almost an infinity symbol. It means proportional to the temperature in Kelvin. And there's a formula related to it. That's Ke equals 3/2 kBT. That's how kinetic energy is related. And then, of course, kinetic energy is 1/2 mv squared. So 1/2 mv squared equals 3/2 kBT. And that's how we can see that motion, velocity, and temperature are related. That's trivial for our course, but it's worth mentioning, especially just for clarity. Neat. So let's proceed onward and upward. Nature of gases continue. Gases expand to fill their containers, and the way I went about explaining this, pointing this out, was that we were going to, we said gases fill their containers, just to be briefer. Can't make it go. They are fluid, so they flow. Gases have a low density, and this is just a trivial point. It's 1/1000th of the density of the equivalent liquid or solid. It's just a different phase. They're so spread out, the density is lower. And gases are compressible. Gases effuse and diffuse. Effuse means to spread out. Diffuse means to spread across, like a boundary or a border, something permeable to the gas. Anyway, these are the nature of gases. This nature of gas leads us to an interesting point. The interesting point is that gases themselves are interesting, which is why they were studied, which is why we have this whole unit about it, because their molecules are so interesting. That's why we're going to dive right into it. Scientists thought they were interesting as well, and they gleaned some certain factors. By manipulating these various features of gases, they've been able to determine some interesting findings from there. And so, back to our foldable on the inside. We have pressure, volume, and temperature. This is a picture of William Thomson, or Lord Kelvin, as he's more affectionately known. Pressure, of course. It's a force caused by the collision of the molecules with the wall of the container. Oops, there goes my pencil again. Sorry. Oops, there it goes again. Okay. Collision of particles, force caused by the collision of molecules with the walls of the container, therefore lending to the pressure expressed or produced by the gas. Okay, so measuring pressure. First pressure was measured by Evangelista Torricelli in the 17th century. The device was called a barometer. Baro meaning weight, the root word meaning weight, and meter meaning to measure. A barometer looked about like this. It was a skinny glass tube with a capillary effect going on. Skinny glass tubes, capillary effect. You can see this. The effects are similar to what you do when you stick a straw in a cup and you put your thumb over the top of the straw and pull it out. Liquid remains inside the straw. There's this sort of space, this empty space. Well, there's just a certain force of the pressure of the gas that was between the straw and your finger and the liquid, and so that gas was creates a little bit of a suction, a vacuum force. Whenever you pull it up out, the liquid wants to remain there, just sort of maintain that pressure the same. Otherwise, it will create negative pressure. That's hence the reason there's suction, and it's enough suction to overcome the force due to gravity on the liquid. That's neither here nor there. It's just an example of capillary force. Another example of capillary force is if you've ever had your cup at a restaurant condense on the table, it gets a little moisture there, and you put your plastic card or something plastic flat next to it, not on top of it, but next to it, some of the moisture would seep in underneath it, and it almost feels like it's glued to the table. You have to pull it to the edge of the table to actually get that plastic card up. If you don't know what I'm talking about, you can try this. Honestly, you just put a few droplets of water slowly, carefully next to a plastic card on a flat container. You can check it out. Nevertheless, that's called capillary force, and that's what allows the adhesive properties of a liquid to slide up a glass tube, a skinny tube, counterbalancing, countermanding the force due to gravity acting on it. Nevertheless, what aids in the rise of that fluid is the atmospheric pressure pressing down on this pool of a liquid. Mercury is the chosen one in this case. That mercury rises up, and at sea level, and generally speaking, throughout most of the year at sea level, so low elevation or at in normal weather conditions, the atmospheric pressure can press down on that fluid, cause the capillary force to increase. The adhesive forces makes it rise 760 millimeters up that glass tube. Standardized glass tube in this case for barometers, but that 760 millimeters of mercury gives us the unit that you may have already written down in your foldable. Because Tor discovered it, he gets credited also with his own units. These 760 millimeters of mercury is the standardized, regular, normal air pressure at any given time at sea level and normal weather conditions, and it's always compared to that number. And because he discovered it, Torricelli, he gets his own. That's also called 760 Tor. You've also hear words like millibars. That'd be like incremental measures put along that glass tube. The number of bars that are counted would be bars or millibars. Anyway, it's also a barometer, so barometer is where you get that. Units for pressure, we got 1 atmosphere. Well, because some areas were using this 760 millimeters of mercury or Tor, 760 Tor, as their baseline standard unit of pressure. We get, there's also another type of pressure that was standard among other parts called kilopascals. It just was accepted by the scientific community to kind of consolidate those units into atmospheres, to say that, okay, this standard amount, let's just make it a whole number, a whole one number. So we would say that at sea level, normal conditions, 760 millimeters of mercury, 760 Tor, 101.3 kilopascals. Those are standard. So let's just call them equal to 1. So the other pressure units didn't go away. They just were added. There was just the 1 was added to it. So we have, these are our various units of pressure that can express pressure. Okay. So atmosphere is just this universal one, and all it ended up doing was, instead of consolidating pressure units, it ended up adding just another unit for us to embrace. So that's fun. You know, nice old, dino, just to add to it. Oops, there's a dancing dog. That's fun. You know how that goes, that kind of stuff. They just kind of make stuff up, hoping to make it easier. It isn't necessarily easy. I don't know why I'm doing all this. I digress. The point of all these units is actually to be able to convert. Now, that just means that this setup, this idea of pressure being expressed by multiple unit types with different values for each one, that just means they can convert back and forth. And that would mean that we would use a T-chart. Let me just do one example for you. I did a couple more in class, but I just want to do one example for you just to see. So let's just say we measured the pressure in kilopascals, or let's say we did it in millimeters of mercury. Let's say we did it as measured at 760 and 40 millimeters of mercury. Oops, let me get that extra hump in the end then. Millimeters of mercury. Okay. We can convert that to any of these other units. For example, let's just do kilopascals because that's the most difficult one per se. To kilopascals, and we want to come from millimeters of mercury. I'm going to write this funny here. Okay, and then we have to relate in this column here, in this column, no, not this column. This column, we have to relate kilopascals to millimeters of mercury. Luckily, we have units to do that. 760 millimeters of mercury equal 101.3 kilopascals. So you can see this 101.3 kilopascals over 760 millimeters of mercury. Multiply, divide, just like any other conversion, and our units will be converted into kilopascals. This is, of course, just using conversion factor, which just means between all of these units, you could put an equal sign. 1 atmosphere equals 101.3 kilopascals equals 320 pascals, which equals 760 millimeters of mercury, which equals 760 torr, because torr and millimeters of mercury are the same units because Torricelli discovered them, thus torr. Anyway, we can quickly see that creates just another conversion factor, and that's what I would say. Add that to your foldable in case you didn't already have it from what I was saying. But notice 760 torr equals 7 millimeters of mercury, 760 millimeters of mercury, which means 1 torr equals 1 millimeter of mercury. What are some examples of pressure? Tire pressure, bottle pressure, sure. Volume, next part of your foldable, the amount of space taken up by an object. No big deal, nothing difficult there. The major units are liters, milliliters, cubic centimeters, and cubic meters. Liters are the most used mathematically, the most used in general when referring to pressure. And if we have any other units, we need to get them to liters. We always need to get to liters if we need to use a constant. We need to match the units. So we always need to convert our volume into liters to make our units match. If they already match, we don't need to convert. You'll know what I'm talking about when we get to it. Same thing goes with pressure. Pressure, if we need to match our units, that's why we can convert. That's why there are 5 different types of units, but the top 2, 1 atmosphere and 101.3 kilopascals, are actually the most commonly used mathematically because they're in our R constant. They're in our R constant. You would have found that from that half sheet referring to the R constant. To clear anything else up, I wanted to bring up this sheet here a little bit in greater detail. Notice in our R constant, we have 2 different R constants. What's the difference between those 2 R constants? Well, obviously we can see that the numbers are different, but this atmosphere here and kilopascals here are 2 different units for pressure. So we need to convert pressure units given to those pressure units, atmosphere and or kilopascals, to match. We need to make them match. That way we can know which R value to use. If we can convert to atmospheres, we would use the first R value. If we convert them to kilopascals, we can use the second R value. It just matters as to what we can convert or what we're needed to match. Also, we can see here that kPa, or liters, moles, Kelvin, are the same in both, and that is because those are the standard units. That there's no argument there. There's no discrepancy. There's no multi-use going on. I know I'm getting a little long-winded here, so hopefully we can just proceed with a little bit more speed. But anyway, I'm already doing it. I promise you, though, there's not much. And truth be told, this is one of the easier, more straightforward units. I'm just spending extra time. So examples of volume, of course, we got bottle volume, liquid volume, and we have like a syringe pulls out a certain amount of volume. Temperature is the average amount of kinetic energy of molecules in a substance, or how fast it's a measure or a reflection of how fast molecules are moving, especially in relative terms because it's a mathematical formula. I digress. The way we need to understand temperature is that it always needs to be in Kelvin. It measures how fast temperature goes. So inside temperature is given to us in degrees Celsius and Kelvin. Those are our standard units. Degrees Celsius has one facet of applications where it's more typically left in Celsius, but Kelvin is used in most, if not all, mathematical setups involved in chemistry. So Kelvin is what we need to convert to. How do we get to Kelvin? It's just the degrees Celsius plus 273. Now that William Thomson, Lord Kelvin, he's the one who discovered the idea of Kelvin in general by saying that when things stop moving altogether, they would have a zero. They should have a zero motion. It turns out that the theoretical calculation for the temperature when molecules cease to move would be at negative 273 degrees Celsius. Well, to standardize that, Kelvin theorized that time or that temperature at which no objects are moving, no molecules move at all, there's no motion at all, I have no velocity. He wanted that to be it's called absolute zero. So the equivalence would be to call that 0 Kelvin. So the whole scale of 0 Kelvin would be absolute zero, and that's equivalent to negative 273 degrees Celsius. So we get our standard from that. Re-listen to that if you need to. Go back and watch it again if you need to understand the theory. But you don't need to understand the theory unless you just trivially want to, which is fine. I like that kind of stuff. But that is just me. So this is bottom line is we need to go to Kelvin. We always need to convert temperature to Kelvin because there is no math that we can do in gas laws unless they're in. So always be sure to convert to Kelvin. Add 273 to Celsius. If in reverse, if for some reason the question might ask you to express your answer in Celsius, then we convert from Kelvin back to Celsius. That's why it's even listed there. It's just subtraction 273. Now, 273 actually isn't really that exact. Turns out that 273 is just an approximation close enough that works almost every. The bottom line is 273.15. But anyway, it's just 273. That's what we. So let's lay these three scales side by side really quick. We have Fahrenheit, Celsius, Kelvin. Oh, wait, Fahrenheit. I forgot about Fahrenheit. That's probably the most common one to you. It's used in weather. It's used on thermometers. It's used all over the place in normal, regular applications besides school, really. But notice how the scales line up. Now, how do we convert to Fahrenheit? Well, I'm glad you asked that. Turns out that to convert to Fahrenheit, we need to say that degrees Fahrenheit equals degrees Celsius times 9/5 plus, and that's all done first, plus 32. Now, you want to get into the history of Fahrenheit, you can look it up on Wikipedia, but that is what it is. That's how you convert to Fahrenheit. It's degrees Celsius times 9/5 or 1.8. 1.8 times degrees C plus 32, and that's how you convert back and forth. You, of course, can go in reverse by doing some quick algebra there, but I'm not going to spend too much time on that. I just think you can. We do it so sparingly, it might be done a couple problems at the most on it. Anyway, I digress, and let's just keep on going. Biggest thing is to take away is, of course, be able to convert to Kelvin and back and forth as needed to Celsius. So what are some examples of temperature? Well, hopefully, I don't list any on this slide because hopefully you can consider some. Air temperature, room temperature, outside temperature, food temperature, oven temperature, right? Core temperature, body temperature, You know, you could come up with any numbers of one. I'm not going to bore you with it, but I will say we need to be in Kelvin. So more on the back, you got the standard temperature and pressure, STP, standard temperature pressure, STP, equals 273 Kelvin or 0 degrees Celsius. We can just add 273 and just remember degrees Celsius. 273 Kelvin is the most important for math terms. Standard pressure are the 5 we listed, but the most important one would still end up being, oops, sorry y'all, moving my screen around too much. I clicked on my pen, didn't go. Would be atmospheres and 101.3 kilopascals because those match the R values that we have going on. But all right, let's proceed. Those are STP. Any one of those, 101.3 and 1 atmosphere are the most, but they're standardized to equal 760 in the 2 different types. So we list them anyway. A mnemonic, you know, it's a mnemonic. So what are you going to do? Is stop. The phrase stop. Okay, because the STP are given to you by 0 degrees Celsius and 1 atmosphere. The exclamation point is kind of acting like a 1 there. I know that's not, you know, super clever, but what are you going to do? It is what it is. It's just, it's there. You still have to remember that you have to add 273 to degrees Celsius to Kelvin. You still have to know that 1 atmosphere is also equal to 101.3 kilopascals. So take it for what it's worth. It's a mnemonic, nevertheless. So we're not gonna split hairs on that. We're just gonna do it the way it says. You know what I'm saying? So there it is. The Go Dogs. But let's keep on going. That is going to take us almost to the end of day one. But first, we have 3 laws to go through. So the scientists, the gases are so unique and interesting. They were studied by scientists, and things were discovered about them. Things that were discovered, we will take a look at, and how that gases respond to certain stimuli, and dependent variables, or how they change when we have certain independent variables and dependent variables, and various explanations. Nevertheless, we have 6. Let me go here. We have 6 equations to consider. We're going to do 3 in this video and 3 in the next, which I know seems a little convoluted. Why don't I just go ahead and finish them all in this video? I won't, because that's not how we break them up. And on these 3 equations, we're going to have 2 sheets of paper to work on, 2 worksheets, where on the front and back would actually be 4 tasks total. So I'm going to upload those shortly with this video, and that's what everyone worked on day 1. The second day we actually talked about gas laws, but I'm calling it day 1 because day 0 was more of an introductory inquiry-based thing and not so much a lecture-style teaching one. Nevertheless, I digress. Let's keep on going right along. Okay, first law is Boyle's law, and it's easiest to consider, or best to consider, our lungs. If you will, inhale with me. Exhale. When you inhaled, your lungs expanded and air rushed into your face. Okay? That happened because when your lungs expanded, the volume went up, which made the pressure go down inside. So air rushed in to fill that low pressure area, because air, just like everything else, goes from high to low. High pressure to low pressure flows in that way. Air flows into the lungs towards that lower pressure. Cool. That's Boyle's law. Or Boyle discovered that. He also noticed that, also what's gleaned from that is that when you exhale, your lungs compress, increasing the pressure on the inside, squeezing air out, or air is forced outward because now outside is a lower pressure, and so air rushes to the outside. This relationship between volume decreasing, pressure increasing, and vice versa, volume increasing, pressure decreasing, is the main thing to consider here that Boyle's law understood. It states that the pressure of a gas is inversely related to the volume when T and N are constant. That just means T and N are not manipulated or changed in these 2 circumstances. They're kept and remain constant. But if you take like a piston with a certain fluid gas inside at a certain volume, and you decrease the volume, the pressure on the inside increases. Decrease volume, increase pressure. This would be an inverse relationship. As you increase one, the opposite happens to the other. And Boyle's law therefore gleans a formula: P1 times V1 equals P2 times V2, or more affectionately described, P1 V1 equals P2 V2. So this video is getting a little long, so I might pause here after the Boyle's law, but this is the first worksheet to go ahead and start on. The bottom line is we're going to do some practice problems first, and then we'll go from there. I'm going to keep this video going for the sake of finishing Boyle's law, but when we get to Charles' law, I might consider breaking it up. We'll see. All right, so first problem here, you can take a look at it. Try it on your own, if you will, because I'm going to breeze through it very quickly. And we're back without further ado. If you didn't pause, go pause and try this on your own. Anyway, what is the new volume in liters of an 8-liter sample of Freon with a gas initially at 550 millimeters of mercury after its pressure is changed to 2200 millimeters of mercury while at constant temperature? Okay. First it says, what is the new volume? What does that indicate? What is the new volume? That indicates that volume changed. So what is the new volume means V2 is not understood. It's not known. Okay. In liters of an 8-liter sample. Okay. That is a known volume. That would be V1. Initially at 550 millimeters of mercury. Millimeters of mercury is the units for pressure. So that's a P. 550 is P. Initially is at the beginning. So that's P1. P1 V1. Then the pressure is changed to 2200 millimeters of mercury. That would be P2. So we need to find V2. We take our equation, P1 V1 equals P2 V2, cleaned by Boyle himself. Plug in the numbers, and we do the basic one-step algebra to solve for V2, and we get 2 liters. Now, in sig figs, it should be 2.0 liters. just to be correct, because our lowest number of sig figs provided is 2. So 2.0 liters should be the answer. We noticed the pressure increased from P1 to V1, or P1 to P2, so V1 should go down to V2. All right, here's another conceptual question now. Let's say initially we have a piston at this volume and pressure setup. Which A or B would it look like if the pressure decreases? What about initially if the pressure increases? Which letter would it be? Pause and think. Have you thought of it now? Okay, because here it goes. Pressure decreases is B and pressure increases is A. Pause and think about that if you need to. Another practice problem, a sample of helium gas has a volume of 120 milliliters and a pressure of 850 millimeters of mercury. What's the new volume if the pressure is changed to 425? So, has a volume, 120 milliliters, that's V1. Pressure, 850, that's P1. What is the new volume? New means 2. New means 2. V2, volume. Pressure's changed to P2, 425. List of variables. Pause if you need to see these things worked out. I'm going to breeze through them a little bit more quickly. Mute me if you need to, because I'm going to click on through as I go. Take the equation, plug it in, solve for the variable, and you're good to go. Two sig figs is the answer, 240 milliliters. We notice pressure went up, volume went down again. Another conceptual exercise. Pause if you need to, read the problem, or just mute me and you can go through it on your own. Let's take an initial balloon with initial volume as pictured, 6.4 liters with a pressure of 0.7 atmospheres. Then it's increased to 1.4 atmospheres. What happened to the pressure there? Went up. And if the pressure goes up, the volume must go down. Which balloon, A, B, or C, reflects a decreased volume? A would be that case. So let's do the math involved with that. Sample of helium gas has a volume of 6.4 liters, pressure initially at 0.7, P1 and V1. What's V2 if P2 is 1.4? Equation, plug, solve, answer. 2 sig figs is our answer. 3.2 liters, check. Notice I didn't convert, or my units there were liters. Earlier I had milliliters and I didn't convert to liters because the units just have to match. We only convert pressure and volume to match the units. We always convert temperature because temperature needs to be in Kelvin, in case you were waiting on me to say that. Cool. Pause and read that if you need to. Another practice problem. Volume of 12 liters at 600 millimeters of mercury. What's new pressure? P2. If the volume changes to 36.0 liters, that's V2. There's the problem for you. Now the number of sig figs is going to be 3 in this case, so it should be 200 point. We put a decimal there after the 200, and it automatically activates those zeros as significant, so 200 point millimeters of mercury is the P2. Take a moment, pause if you need to digest that, read it to yourself and understand it. What about Charles' law? Charles' law reflects on the relationship between volume and temperature, okay? Now that we're in temperature, we need to practice understanding how to convert temperature. So remember, temperature needs to be in Kelvin always, unless the problem asks you for your answer to be in temperature and Celsius, which means you need to convert from Celsius into Kelvin and then convert your answer in Kelvin back to Celsius to satisfy the requirement of the question. But that'll happen as you see. Let's practice first. Remember, to get from Celsius to Kelvin, we add 273. Mnemonic for that is that Celsius is the third letter of the alphabet. K is later, is a further number, a higher number in the alphabet. Celsius, third letter of the alphabet. C is third letter of the alphabet. K is later in the alphabet. So to go from C to K, you need to add 2. So C to K, add 2. So 273. So 25 and 273, 298. Pause and try it on your own if you want to get ahead of me a little bit. 107 plus 273, 380. go from Kelvin to C, I need to go in reverse, subtract. So 500 Kelvin is 227 Kelvin. 227, actually that should be 227 degrees C. I don't know, that was a typo. 100 Kelvin to degree C, subtract, negative 173. Yes, we can get to negatives. That's the whole point of Kelvin, is that Kelvin could be zero, technically. That's called absolute zero, which is negative 273 Celsius. But I digress. So Charles' law, without further ado, says that pressure or volume and temperature are related. And typically it's temperature that's usually managed here. But if you could somehow manage to keep pressure the same, which would be very intense, you have to change the pressure of the surroundings and the inside of the container to equilibrate that a little bit. But if you could keep pressure the same, you could technically increase or change the volume, and that would change the temperature. But typically it's temperature that causes the volume to shift in and of itself. This would be like how pistons work in firing of an engine of a vehicle. Anyway, bottom line is, we notice from this diagram that temperature goes up and volume increases in tow if pressure is made a constant value. So pressure and volume, or volume and temperature, are directly proportional. One goes up, the other goes up, giving us this equation, V1 over T1 equals V2 over T2, with pressure in moles constant. That'd be pressure and concentration constant. Same sort of setup is, here's a problem. We have a balloon has a volume of 785. That's V1 at 21 degrees Celsius. That's T1, but it needs to be Kelvin. So add 273. Temperature drops to 0 degrees Celsius. That's T2, but it needs to be in Kelvin. So plus 273. That's standard temperature. That's interesting. What is the new volume? That's a question mark. We take our equation. Pause, slow this video down at any time, of course. Sidebar, to make sure you understand what you're doing. It's just so you can really clarify. But we plug in. Now, one extra step before we go back and do the exact same math as the P1V1 equals P2V2 equation. We've got to get to that format, so we need to cross multiply and divide in order to get it. Now, you can probably notice that you don't have to cross multiply both sides. You can technically leave the 294 on the bottom the whole time and only cross multiply the 273. If that makes sense to you, or you discover that on your own, that shortcut, you can use it. But understand that you can only use shortcuts that always work. If you use a shortcut and it fails you, you can't use a shortcut anymore. I don't trust you to use them. So don't use a shortcut. Just cross multiply and then do the same exact step for the P1V1 equation. Answer 729. Sig figs are 3. By the way, we don't look at sig figs in the degrees Celsius. Degrees Celsius does not tell us sig figs. We need to get to Kelvin. That's all we can judge for sig figs. Cool. So another problem here. Sample gas volume of 420. V1. 18 degrees Celsius. T1. Got to get to Kelvin. Of course, you can always mute me and let me just slide along here. V2 is 640. T2 is a question mark, but it asks to be in degrees C, so we have to remember to go back to degree C. At the end, plug in the equation, write the equation, plug it in, cross multiply, solve for T2, we get in Kelvin. But we're not done. The problem says in Celsius, so we must take the additional step and get it to 170 degrees Celsius. We want to check sig figs in the Kelvin. We're going to do whatever happens after the Kelvin in Celsius and leave it as it is. We're not going to worry about sig figs in the degrees Celsius. Once again, we're not going to worry about sig figs in the degrees Celsius. Let's keep going. That's Charles' law. What about the last law, Gay-Lussac's law? Gay-Lussac's law. Joseph Louis Gay-Lussac. Anyway, he discovered the relationship between pressure and temperature is directly proportional as well. P, so that lends the same equation as the V1, just with P instead. When you keep pressure constant and you increase temperature, pressure also increases. I'm sorry, when you keep volume constant and you increase temperature, pressure also increases. And vice versa, this happens in reverse as well, although it's harder to maintain things whenever you're increasing pressure because typically that involves a volume movement. But I digress. Same equation, same sort of setup. Let's get to it really quickly. Keep on going. So next problem here, we have a pressure of 2 atmospheres. That's P1. 18 degrees C, needs to be in Kelvin. New pressure, we don't know. T2 needs to be in Kelvin. Plug it into the equation. Cross multiply to get it to the one step away. Divide by to to solve for P2. We'll get 2.3 atmospheres. The sig figs would be 2 sig figs. So that is done in there. Notice it didn't convert pressure into millimeters of mercury or anything else because it was already matching. We just needed to match atmosphere and atmosphere. We have it seen at least twice. We're good. We just need to match it in that way. Cool. Another practice, 645 torr at 128 degrees C. We don't know T2. Notice the pressure given to us and the other pressure is 1.5 atmospheres. We have to convert to torr to make them match. We don't know T2. We plug it in. We solve. We get T2. And then in degrees Celsius, we subtract 273 to get it degrees Celsius. Done. Dalton's law is the next equation we're going to touch on in the next video. So for now, I bid you adieu. Hopefully that gets you set up. I know that was kind of a longer video. It probably took a little bit longer on the video than in class, but ultimately my next thing I'm going to tell you is the task list, and this unit's more or less self-paced. So get straight to the worksheets that I've attached with this video. They're linked. They're here. And go to it. Get straight to it. Don't waste another minute. I'm going to post the other ones, the next worksheets with the next video. Everything's kind of self-paced. You can go with the flow. From there, I'm going to post a picture of the task list and the instructions that go along with that. So look forward to it. It's coming soon. Could be on the same post of this video. We'll see. It might probably be with the very beginning of the next video. Just show that task list as promised. So Godspeed and go dogs.